Alright, my dear children of class 11 science, we do continue with the topic that is viscosity. The chapter we have studied is called flow of liquids, and in this particular YouTube video we do a very important topic, that is velocity gradient and coefficient of viscosity. So in the last YouTube video you learn in detail about the viscosity, what is viscosity, the example of viscosity and all. Okay, now we have a next topic related to viscosity, that is called coefficient of viscosity. But before that we try to understand velocity gradient. Now for that I'll take the liquid which is flowing in a particular direction. And what type of flow of liquid I consider? Streamlined flow of liquid I consider. So as children, as I said, like the flow of liquid are two types. One is called streamlined flow, one is called turbulent flow. But in this chapter we focus basically with streamlined flow. And the definition of viscosity and the expression of this coefficient of viscosity is actually derived for what type of flow? Streamlined flow. Now I consider a liquid, any liquid which is flowing in a streamlined motion, and the liquid is flowing on this surface. This is a horizontal surface. OX is a horizontal surface. Okay. Now liquid layer in contact, as you know, liquid layer in contact with the surface, okay, is at what? Rest. While the velocity of other layer increases with the increasing distance from the surface, that is OX. That what we have learned already in the last YouTube video also. But you know, children, that the highest layer flow, okay, with maximum velocity takes place on the upper surface of the liquid. What surface? Upper layer surface of the liquid. Means the layer of liquid which is flowing on the topmost layer have maximum velocity. That liquid layer flow with the what velocity? Maximum velocity. But children, you know that liquid has, the layer of liquid has been divided by number of layers, and every layer acquire a velocity. But when we go from one layer to another layer, the velocity changes, and this change in velocity per unit length of the layer, okay, is expressed by the term known as velocity gradient. Now in order to measure the velocity gradient, children, now let me take two parallel layers. So one is PQ, just giving the name, another say RS. So these are the two layer, only two layer I have taken, adjacent layer. Okay. Now this layer PQ, say consider, is at a distance, say Z, from the horizontal surface. This is the surface along which axis? Horizontal axis, x-axis. But this is the surface, the length which we are taking along z-axis. So the distance from this PQ, one of the layer, to this OX surface is what? Z. Now definitely there is a gap between this distance between these two layers, and that distance is very small, and I consider that is delta Z. If this distance delta Z is the distance between the two adjacent layers, then what is the distance between the layer RS from OX? Yes, we can calculate that layer distance, and that is Z plus delta Z. So look at it, the distance from RS layer to OX is Z plus delta Z, whereas the distance from PQ to OX is Z. So what is the distance between the two layers PQ and RS? That is delta Z. Now I consider that this layer, the particle on this layer which are flowing with a velocity, okay, and this velocity is I consider as Bx. So all the particle which are flowing in this layer is acquiring a velocity, that is how much? Bx. Then definitely the particle which are flowing on the above layer acquire a velocity which is more than this velocity, because the distance increases means velocity also increases, and that velocity I consider as Bx plus delta Bx, where this delta Bx is a change in velocity between the particle between the two layers. But what is the velocity of the particles which are flowing on this layer, upper layer? Bx plus delta Bx. So children, we can now easily calculate the change in velocity between the two layers, means at a perpendicular distance of delta Z, and that change in velocity in a perpendicular distance delta Z is nothing but delta Bx, and that's why this sign delta is called change. But this change is a what? Definite change. A change in velocity with this perpendicular distance is called delta Bx. Thus the change in velocity with perpendicular distance, that is delta Z, to the direction of flow is given by delta Bx by delta Z, and this change in velocity per unit distance is simply called as velocity gradient. This quantity is called velocity gradient. So children, velocity gradient in this particular case, which I am giving the example, is given by delta Bx by delta Z, and this is actually called velocity gradient. So when there is a streamlined flow of the liquid, then we can always measure the change in velocity per unit perpendicular distance, and that change in velocity per unit perpendicular distance is actually called as velocity gradient. We call as what gradient? Velocity gradient. Now this velocity gradient can also be measured by the unit, and you can easily guess what is the unit. The unit of velocity, change in velocity, is meter per second. The distance unit is length, so meter cancel out, so the unit is per second. So what is the unit of velocity gradient? Per second. So if this is a unit, then dimension also we can write. Okay, dimension also we can write. The dimension of what gradient? Velocity gradient, yes. So children, we can write even the dimension of velocity gradient as how much? T minus 1. T minus 1, because unit S is for time, unit of time, and time dimension is T with minus 1. So if you see this dimension of velocity gradient, which is similar to the dimension of frequency. So frequency and velocity gradient has same dimension, because frequency dimension is also T minus 1, whereas dimension of velocity gradient also second minus 1. Now the next thing that we measure, we derive the expression is the force, which basically called the viscous force. And with that viscous force exerted between the two adjacent layers, we can measure a factor called coefficient of viscosity. Okay, so for that, let me take these two layers only, adjacent layer only. So every layer has an area. Every layer has what? Area. So let us consider a liquid layer of area. Let me just consider liquid layer has area. Okay, let me show you separately out here. Suppose this is the layer of the liquid which has area A. So what is A? A is the area of cross section of the liquid. Now this layer of area A is at a height what? Z. Same height. That means this layer, I am talking about this particular layer PQ. This layer has area A. So basically what happened, that there is another layer above it. So the layer of the liquid immediately just above it tends to accelerate it. It tends to accelerate, it means tends to accelerate the velocity of the what? Of the particle of the liquid which flows in this layer. Okay, with a tangential viscous force, and this force exerted in this direction. But there is a layer just below this also, and that liquid layer below it try to oppose the layer with a force, same force, and this force acting in this direction. So this force try to accelerate the layer of this particle of the layer present on this layer, that is PQ. But there is a layer just below that, that layer also exert a viscous force in a direction opposite to what? This force which try to accelerate the layer. But this viscous force, okay, try to retard the what? The motion of the particle on this layer, that layer of area what? A. So according to Newton's law, as we have learned, according to Newton's law, the viscous force F, this is F is the viscous force acting between the two layers of the liquid flowing in streamlined motion, depends upon two factors. That means this force can be measured on and depend and can be expressed in two factors. And one of the factors that you can see is this viscous force is directly proportional to the area of cross section in which the two layer liquid are in contact with each other. That means force is directly proportional to what? The contact area of the liquid. Means more the area in which the liquid flows, more the viscous force exerted between the two layers. That means F is directly proportional to A. Similarly, this force is also directly proportional, okay, proportional to the gradient, and that gradient you have learned already is called velocity gradient. That is given by delta Bx by delta Z. More the velocity gradient between the two adjacent layers, more the viscous force exerted between the two layers. That means this force is directly proportional to area of contact in which the liquid flows, and this force also directly proportional to the velocity gradient between the two layers of the liquid. So if I combine these two equations, both sides, so I can write F is proportional to A delta Bx by delta Z. So see, if you combine this, you can write F is proportional to A delta Bx by delta Z, because both are directly proportional. That's why F can be proportional to A delta Bx by delta Z. And children, you know very well that when there is a when you remove proportional sign to what equals to sign, you have to put some constant. So what I do, I remove proportional sign to equals to sign, so I put some constant, and that constant is given by this sign, and this is actually called eta. We use this symbol as eta, a delta bx by what, delta z. And this sign symbol which we have used is actually a constant of proportionality, okay, and which actually depend upon the nature of the liquid, nature of the liquid. And this constant of proportionality, which we have expressed in the expression of viscous force, is basically called as coefficient of viscosity. This is basically called as coefficient of viscosity of liquid. That's why, as I said, this sign eta is actually called coefficient of viscosity of what, liquid. Okay, so I'll put plus minus sign also. So in the expression I put plus minus sign.